So this is the question from 2025 JE Mains paper. And before we begin, let me just uh, tell this the most softest way from my end. In fact, I don't think there is any softer, even softer way from that's possible from my side. This is going to be a really long solution. You might be wondering what is so in it to make it really long. Uh, in 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 my opinion, right? In my very personal opinion, see, I'm not a subject matter expert. I'm not a physicist for that matter. I'm not even a JEE mains expert. But what I'm trying to say is the whole series here, the complete program is based on the relevance of PYQs and, of course, the concepts that make the PYQs. In that perspective, this is a stunning question, in my opinion. Very stunning question. Each and every graph here has a lot to convey. It has many things that can later be, you know, sound to look like it is based out of these questions in a very distinct way. But all the concepts would actually be based on this, but then it would sound that it is completely a new question altogether. So each and every graph here has to be given its own weightage, and we'll try to do justice to equal justice to all the graphs. Okay. So there are some things that would be better understood when we go through the presentation, and some of them has to be written, handwritten, and you might also want to write it down, follow the notes along with me so that things make more sense. Okay. Right. So give me a second, let me just go through a couple of more things. Okay. So we've been given four graphs to find what is one dimensional motion. So we first have to understand what one dimensional motion is. A motion is said to be one dimensional if a particle moves along a single straight line so that only one spatial coordinate is sufficient to describe its position at all times, either along x or along y. So, those who are here for the first time, perhaps those who are starting this program in 2025, this would be your first question in the complete series of solutions, right? So, I assume you're starting with a fresh book. And of course, the index has followed as we said the reference section. So I would actually suggest that you can make a note of these things because this would help you a lot in answering the statement one, statement two type questions. Oh, I think you already have gone through the introductory video, so that shouldn't be a problem. But I would suggest that you make a note of these. Okay, right. Now, in one-dimensional motion, physical quantities such as position, velocity, acceleration, or phase. I have taken phase here very specifically because the first graph is based out of phase. Well, usually you don't find these definitions included in phase included in these kind of definitions. So in one-dimensional motion, physical quantities such as position, velocity, acceleration, or phase are single-valued functions of time. Now, this is one particular thing which will need a significant amount of understanding, which demands significant amount of understanding about the concepts of relations, limits, continuity, and functions. Okay. Now, to cover all of that in this solution is going to be it's a really painstaking effort, both from my end, your end as well. So I don't think that's good enough to do that. So having said that, it goes without saying that there will be a definite amount of, you know, not understanding things throughout the solution, even after we follow the notes till the handwritten ones. There will be certain amount of things that certain amount of concepts that we are not familiar with that you need further clarity in, and all of that cannot be solved in one question alone. But trust me, after the end of the complete chapter, going through all the solutions, you will have a very good stronghold of the concepts. And then you'll understand, oh, so this is what the first question was all about. This is what functions was being referred in the first question. Okay? Right. Therefore, any given time, each of these quantities has only one definite value. The key point, the key takeaway from this point. Therefore, for any given time t, each of these quantities has only one definite value. Okay? As a result, the graphs plotted with the time on the horizontal axis. Exactly, I'm trying to take you through the problem alone. That's why all the definitions are merging back to graph. The first paragraph had a reference to phase because the option here had a phase in it. The second paragraph is actually about definite values, only one definite value, because the whole graph is about finding which graph satisfies that condition. The time on the horizontal axis, such as position time or velocity time graphs, must not show more than one value of a physical quantity at the same instant. Let's read that one more time if you have written this along with me. As a result, graphs plotted with time on the horizontal axis, such as the position time graphs or the velocity time graphs, must not show more than one value of a physical quantity at the same time. Doesn't make sense? I understand that. Please be patient. We'll go through a couple of diagrams and then things will become really clear to you. So this is a pictorial representation of one-dimensional motion. There's an object here which is moving along the positive x and the positive, or the positive or negative x, could be along positive y and negative y as well. And at every time instant of time, t1, t2, t3, and t4, it is either moving away from negative x, or is it moving, or so it can either move away from x like this, or it can move away from 0, or it can move away from 0 towards x, negative x, or it can move towards 0 from positive x, or it can move towards 0 from negative x. This is how we specify the directions. Okay. And at every instant of time, there can be only one corresponding position and one corresponding velocity and one corresponding acceleration. At every instant of time, there can be only one position, one corresponding velocity, and one corresponding acceleration. At every instant of time, there can be only one corresponding displacement, corresponding velocity, corresponding acceleration. One more time, please. At every instant of time, there can be only one corresponding displacement, corresponding velocity, and corresponding acceleration for this particle. Okay? Okay. Now, the particle state at any time can be described by just one variable, which could be either position or phase. Okay? For every time, there should be only one value of phase, something that we discussed right now. Only one value of phase or velocity, which means time corresponding to one phase, or time corresponding to one velocity, time t2 corresponding to another velocity, or maybe time t3 corresponding to another velocity, or t4 corresponding to a new velocity. Okay, so there should be only one specific velocity corresponding to an instant of time. The graph should never loop back or repeat values at the same time. At this point here, the graph should never loop back to repeat values at the same time. This is really important. I would suggest this is the important thing in the first graph, looping back of values. And yes, I'm not saying that I expect very strongly a question from this point here, but something based out of this. Yes, I would suggest that. So these are the graphs we have: space time, velocity displacement, velocity time, total distance, and total time. Okay. So we'll first focus our complete discussion on space time. Now, what is this graph showing here? It is showing the plot of phase versus time. So even though phase is not itself a position, if it smoothly increases over time, and if it's used in a function like x of t is equal to a sine of phase, right? Sine argument phase, the resulting motion is a one-dimensional motion along a straight line. Okay. So yes, this graph actually corresponds to motion in a straight line, motion in one dimension. Now we'll have to spend some time to understand what this graph is actually about. So we will be given a straight line graph. X-axis is time. What is the y-axis? It is phase. And the actual curve here is a line that starts below zero here, and it is increasing steadily upwards. Okay? It is increasing steadily upwards. Now what we'll do is we'll read this graph as an equation. See, what I'm trying to do here is I'm trying to, you know, take you through the process of understanding a given graph and trying to make sense in a mathematical and a physical way out of these graphs. Okay. Yes. See, I do understand that you have a lot of questions here. Perhaps only questions, and that all of them would not make sense. It wouldn't make sense to answer all these questions right away in the first solution that you're watching. One of the side effects of one of the negative effects of reverse engineering. so so please bear with me. Please follow the solutions with utmost patience. Trust me, the process will definitely be rewarding you with concepts that will stay with you for a very long time. Okay, not just for a JEE means, even beyond that. Now, given the equation of a straight line, if we compare that with the standard graph, which is y is equal to mx plus c, so we're going to compare the straight line that we have in this option A to y is equal to mx plus c. Now, if we substitute these quantities, what we actually get is, instead of y, we have phi, the phase, mx, omega t plus c. The slope here is omega, right? And c is the phase at t is equal to 0, which is the y-intercept, although not this graph. It's a different graph. So if we compare these two graphs, that's what I'm trying to do here. Y is phase. I hope that makes sense. X here is time. And run and rise, or in other words, the slope here is omega. Okay? Mathematical equation of a line, comparing those two with a given chart. Now, what does this graph show here? The given one. The graph is a straight line, of course, and it is increasing uniformly with time, which means y is increasingly with respect to time, phase is increasing with respect to time uniformly, and the slope is constant, which actually means uniform motion. The slope is constant. Now, when we say the slope is constant, it means constant angular speed. The line starts below zero. Very important. The line starts below zero, which means the y-intercept is negative here. And when the y-intercept is negative, it means that at t is equal to 0, the phase is already negative. Oh, sorry, the phase is negative, which indicates that the oscillation has already started in the past. And now you're like, what is oscillation? Please, please bear with me for some more time. C less than zero, it means that the phase is already negative. It actually has to do something with this diagram here. This is time t is equal to zero, and this is the amplitude. This height is the amplitude, and this represents the portion of the wave before t is equal to zero. Okay, that means the oscillator had already moved part way through a cycle, or maybe less than a cycle, before the time began. In simple words, you started your stopwatch late. That means the system was already oscillating before we began measuring. So, say for instance, this was here at t is equal to 9 a.m., and this swing is here in say t is equal to 9 1 a.m. I do understand it's not a practical example, but just trying to make a rough example here. So 1 minute later, the swing has moved from say this position to this here. But then the observation started only at t is equal to 0. My bad. The observation started t is equal to 9 1 a.m., which means this 9 t is equal to 9 1 a.m. is actually t is equal to 0 in physics. So this is where the actual observation starts, if that makes sense. Okay? Right. Messy, I do understand. Sorry. Okay. So this is what I was talking about the graph previously. At t is equal to 0, the phase is already negative. That means the oscillator had already moved partway through a cycle, or maybe um, okay, through a cycle is it sounds a bit incorrect there. It may not be always through a cycle. Okay, feel free to skip this part before the time began. So this is when the wave was seen after we started observing it, which is at t is equal to 0. But the wave was already moving before we started the actual observation. Okay. Now it's becoming overwhelming, right? I do understand phase, oscillation, all of this in the just first question of 2025. Yes, I do understand. It's a bit difficult to follow. So we have a wave that is moving along the y-axis, right? So we have a wave moving along the y-axis. I'm sorry, moving along the x-axis, which is time. So we started at t is equal to 0. And if you see, and if you note here, there is already some motion. And after at t is equal to 10, the wave has progressed towards the positive x-axis. So the actual observation is happening only after t is equal to 0. But what has already happened is some amount of previous oscillation before that. Okay. Now, does phase describe a motion along a straight line in reality? Yes. In oscillatory motion, like simple harmonic motion, phase is the internal parameter that determines. My bad. So, in oscillatory motion, like simple harmonic motion, phase is the internal parameter that determines motion along a straight line, like a mass on a spring or a pendulum in a small angle. Okay. So, Say, for instance, if you use the formula x of t is equal to a sine argument of phase, well, this is in particular a sine omega t plus phi 0, then the actual motion x of t will always happen along a straight line, even if the phase itself is rotational, the analog from circular motion. Okay. Now, another point to be noted here, if a graph plots position versus velocity or velocity versus acceleration, it can suggest, not always, it can suggest 2D, two dimensional motion or more, something that we don't need now. We'll discuss this in detail while we go through the topic motion in a plane. Okay, but this is definitely relevant to the given question here. So, yes, the first graph here, it makes sense. It is a one dimensional motion. Okay. Now, what we'll do is we'll also write down a couple of things along with this right away. All right.